Okay, number one. But first, let's do a baseball card. Okay. So far we've done Tony Gwynn, Michael Jordan, and Kobe Bryant. This is an iconic baseball card. It's Ken Griffey Jr.'s rookie card, 1989 Upper Deck. I bought an old pack and scored that one, probably on my fourth pack. But anyway, Ken Griffey Jr., let's talk about him real quick. Played for the Seattle Mariners. He was a center fielder. He had this beautiful swing. He hit for power. He had a good career average. And he just had the smoothest swing. I don't know for sure, but I don't think he got caught up in the steroid era. But anyway, 89 Upper Deck, Ken Griffey Jr. All right, here we go. Number one, this diagram right here is a straight edge. So, for example, straight edge. And compass construction. That just means they used compass for the circle and straight edge for the line segments. A is the center of one circle. B is the center of the other. Explain how we know that triangle ABC is equilateral. I like to use color just to emphasize some things. So they're asking you about this one. Why is this triangle, and we name a triangle by their points. This one has A, B, and C, so it's called triangle ABC. Anyway, how do we know it's equilateral? Well, you need to know what equilateral means. So let's highlight equilateral. Now for equilateral triangles, they have their lateral sides or lateral edges are all equal. So equilateral. So the lateral sides are all the same length. So how can you prove that AB is the same length of BC, which is also the same length as AC? So if you can say AC equals AB, which equals BC, then you are done. Now I'm going to give you some word banks, some words for your proof. Use these two words, circles and radius. Circle is a set of all points equal distance from the center. A radius is the distance from the center to any point on the outer edge of the circle. And radius will be the same length in a circle. So, for instance, there's a radius of circle center A, AC. AB is a radius of circle center A. So you can say that like AC equals AB. All right, that's the first one. Number two, here we go. A, B, and C. A, B, and C are the centers of the three circles. So there's a circle, center A. There's a circle, center B. And there's another circle, center C. How many, here's where this comes up again, equilateral triangles are there in this diagram? One to look out for that you might miss is the bigger one. You can prove this orange triangle is equilateral because there's 3 sides of this orange triangle: DH or HD, HF or FH, and FD. And if you look at the orange triangle, there's a radius and another radius. So these are 2 radii. Notice that all the circles have the same radius. AB will equal AC. AB will also equal BC because they are, let's go with the word bank. So use this word, radius and circles. Now, when you're proving equilateral, you also want to use the same length. So the key on this one is how many, though. I gave you one, the orange one. You got to find all the equilateral triangles. Okay, number 3, here we go. This diagram, this one, is a straight edge and compass construction, which means all the lines we used a straight edge, like the bottom here. And then all the circles we used our trusty compass. That's what that means. A is the center of one circle, and B is the center of another, or of the other. Select all. That's an important one. Select all. That means that there's going to be more than one, most likely. So select all true. Okay, let's just look at them. Does AC equal BC? That's A. Let's look at B. Does AC equal BD? Let's look at C. Does CD equal AB? Let's look at D. A, B, C, D. Well, look at the order. First of all, you want to go in order when you're talking about a square. They're going across and then up and then across. That's kind of weird. That's a first indicator. And then let's look at this one, ABD. So ABD, this triangle right here. Is that one equilateral? And then lastly, CD equaling AB plus AB. Okay, well, let me show you a little trick on this last one, which is F. Let me show you something that might help with the logical reasoning. Let's just look at this. AB plus AB, that'll be 2 radii, right? Which is kind of like the same thing as, let's just label this E and F. AB plus AB will be the same thing as EB plus BF. 2 radii. So, does CD equal EF? All right, there's 3 for you. At 9 minutes, pretty good pace here. Let's go to number 4. Line segment, that's a keyword. Remember, line segments have a starting and ending point. So line segment CD is the perpendicular bisector. Might want to underline that. of line segment AB. Perpendicular bisector. It's a line that's perpendicular to a line segment. So AB is your line segment. CD is perpendicular. That means it forms a 90-degree angle with AB. It also bisects AB, meaning this has this MB has the same length as MA. Okay? So is line segment AB, here it comes again, is it the perpendicular bisector of CD? Well, takes a little bit of reasoning, but let me help you a little bit. So remember, CD created two line segments that were the same length and formed 90. Let's tilt this or rotate it. Now, AB does form a 90-degree angle with CD, but does this have the same length as this? You tell me. Okay, number 5. Here are 2 points in the plane. Okay, so A and B. Now, we're not talking about an airplane. We're talking about the plane. We'll get to that in a little bit. But here are 2 points in the plane. Using only a straight edge, can you find points in the plane that are the same distance from points A and B? Explain your reasoning. Using only a straight edge. Okay, so let's just imagine that we just have this Michael Jordan card, right? Now, we don't know distances on the plastic card, right? We just have a straight edge that helps us build lines. Now, using only a straight edge, that's a key point. Can you find points in the plane that are same distance from A and B? I'm gonna try one. I think I can do it, but I'm not sure I can get them all. So let me see here. So I drew this line to help us out. Sorry, line segment. Even I make mistakes. That's a line segment, not a line. But one thing I could potentially do, I think I've drawn the line segment. I could fold it over so that B and A line up. That's one way to do it. Let's see if I can do that. It's really difficult, actually. Let me see here. I can't really see through, but you could fold this like so that B and A line up, and then you're gonna have like a fold in the middle of the paper. So that's one way that you could get like the midpoint. You could technically measure using your straight edge. I guess that's a way. So AB is 3.5 centimeters, 3.5 centimeters. So AB equals 3.5 centimeters. You could divide that by 2, end up with 1.75, I believe, on each. Let me just triple check. 3.5, 1.75. No, that's wrong. Let me think. 3.5. I think it would be 1. Let me just divide that by 2. Hey Alexa, what's 3.5 divided by 2?
3.5 divided by 2 is 1.75.
Cool. So it would be like right here, technically. So you could find 1, and then you could use your protractor, find the 90-degree angle, connect the dots, but I mean, technically we're getting out of it. Just imagine you only had a straight edge, right? Like the edge of the Michael Jordan card. You don't have a protractor feature. So anyways, I'm gonna say yes, but there are limitations. All right, let's look at B. Using only a compass, can you find points in the plane that are the same distance from points A and B? Explain your reasoning. Well, for this, you would have to do what's called the perpendicular bisector construction. And I'll show you how that would work. So let's create some room here. All right, so say I did something like this. I mean, I guess you could, right? Because you know what a perpendicular bisector does. It creates a line or line segment that represents all the points equal distance from A and B at the same time. That you may remember from class, I hope. So you could go like that. And then like this. And that's just a compass, right? And then you could find that point and that point. But they say using only a compass. I wouldn't be able to use a straight edge to make this line. So, I mean, I'm gonna say no, because you need a straight edge, right? That's pretty close to a straight line, but if you look really closely, that's not technically a straight line because I didn't use a straight edge. So, you could get, it just says, can you find points in the plane that are equal distance? These two for sure. All right, so I say yes, but again, but there are limitations. The key on this is really think about these and come up with a justification. It's really important. All right, let's move on. Number 6, here we go. In this diagram right here, line segment CD, so remember line segment, keyword, has a starting point and an ending point. And use a straight edge to connect them. They're saying CD, line segment CD, is the, there it is again, perpendicular bisector of line segment AB. Line segment AB, starting point, ending point. So they're saying CD is the perpendicular, so remember, perpendicular bisector forms a 90-degree angle, creates two line segments with the same length, so AM and BM. Okay? Assume the conjecture. That's another word, conjecture, that you need to know. It's like an educated guess. Something you're trying to prove. A lot of new words being thrown at you. I'll try to explain what those mean. So conjecture is an educated guess of something you're trying to prove. So assume that the educated guess that you're trying to prove, that the set of points equal distance from A and B is the perpendicular bisector of AB. Okay. So then they ask us to do this. I'm going to zoom out a little bit. Hopefully this will be visible. All right, here we go. Does AM equal BM? So you have to select all the statements that must be true. Does CM equal DM? Must be true. Does EA equal EM? We're talking about the length of EA. Does it equal EM? Is EA less than EB? That's what this symbol means, less than. Is AM less than AB? And finally, is AM greater than BM? So you have to select all true. Okay, let's go to 7. Let me zoom back in. Got more room. See if we can fit this whole thing in there. They're really cool problems. Okay, 7. The diagram, this one, was constructed. It's like the same thing as like built. Using straight edge and compass tools. Compass creates circles. Straight edge, lines and segments. Name all segments. If they say just segments, they're talking about line segments. So you got to name all line segments that have the same length as segment AC, this one right here. So you got to find all line segments that have the same length as AC. Okay. Well, radius. There's a radius. Anyway, that's what you need to look for. Radius. Do all circles have the same radius? Well, let's look at center A. The radius is AB, right? Let's look at center B. The radius is also AB. Isn't this a radius? So let's look at circle center E. If AB equals BE, then BE equals AC. And then this is also a radius. So that kind of gives you the answer, but the key is you have to use the word like radius in your justifications. All right, let's move on to the next. Number 8, starting with 2 marked points, A and B. Describe the straight edge and compass moves. This basically means the steps required to construct quadrilateral ACBD. Hey, they used the right order. ACBD. So how did we get here? You gotta write all the steps down. Now, just for fun, I wanna do it. And I think I can if I just use these same points. I'll say A and B. That's what we're starting with, right? So let's do it real quick. So this is step 1. So 1 is draw. 2, and I'm going to give you the number of letters. Label them blank and blank. Okay, so draw 2, and I'll even give you the first letter, P. Label them A and what? Okay, now, should have done this a little bit differently, but that's okay. So we're gonna do this one. I'm gonna knock out 2 steps in one. Hopefully you can watch me do this. Okay, so number 2. Construct a blank center blank radius blank. That would be the second step. Then we do it again. Construct a circle blank B blank AB, right? That was the 3rd step. Now let's go to the 4th step. Label the long word the blank points of the circles blank and blank. One more step. Draw line segments blank, comma, blank, comma, blank, and blank. Here they are. What's this line segment called? What's this line segment called? What's this line segment called? Here, what is this line segment called? We'll just use the same color. There we go. This gives me a chance to talk about what a quadrilateral is. Technically, this wasn't shaded in, but you might even add this step. Shade in give me the first letter. This is a 4-sided polygon. All right, so this whole thing with all your fill in the blanks, which you're gonna have to figure out, is your answer to describe the straight edge and compass moves required to construct quadrilateral ACBD in this diagram. All steps are here. I redrew it for you. Okay, number 9. In the construction, this one. A is the center of one circle, and B is the center of the other. So look for the circles. There's 1. There's 2. One of the circles has center A. One of the circles has center B. Which segment, keyword, that's a starting and ending point, using a straight edge to connect them. So which segment has the same length as AB? So what you're going to need to do is find the radii. Radii is just the plural of radius. Now I will tell you this, both circles have the same radius AB. So if you find a radii of either of these two circles, it will have the same length as AB. And that's a really big learning target from Unit 1, Lesson 2. So there you go. Hopefully that helps. You have to find one of these four that has the same length as AB. All right, nice work. About 30 minutes.